All right, so I've started the recording, so we're officially begun. All right, so everyone, I emailed all of the tests back. So and I replied to whatever email address you send it to me through. Although some people some people send it to me more than once on different email addresses. So I don't know. You'll have to find. I'll have to look because I did reply and attach your graded test, right? So and then the grade, of course, is also entered in WebAssign at this time. So most of you guys did that are logged on here did okay, or some of you did quite well actually. So we had several A's, so that's good. And then uh, on the other hand, though, some people didn't score as well, and so so we're running out of opportunities here to improve our test scores. If you're one of those who didn't score well, or some of you were quite borderline, so you did okay, but you probably could have prepared better for the. You probably could have prepared a little bit better for the test, and then some people were not. I don't think very well prepared at all. So, but I think from your own circumstances and from your test score, how much you prepared or how well you think you prepared. My recommendation for those people, since we are really running out of opportunities to improve our average, right? We've got a third test, and then we do have the final exam, but you really need to take advantage of Madison's SI sessions. So that is really a great way to improve your scores in the class, right? In particular on the next test, and then I'm sure Madison will have someone will have a final exam review session as well. So I really encourage you from now until through the end of the semester, and we've only got 3 weeks left, right? Actually 2.5 weeks left, including today.
Yeah.
So to really concentrate on, really try to attend Madison sessions as much as possible, right? And now, however, also on Thursday at 1:15, so right after class, I'm going to post a makeup exam for this exam. And so it will be it's a short makeup. It's not a full a repeat of the exam, but there will be questions on the makeup like questions on the exam. And so I will post that at 1:15 on Thursday, and then you will have till Friday, so you won't have the full 2 days, but then Friday that will be due Friday afternoon, sometime Friday afternoon. So I didn't decide quite on the due time, but it will be Friday afternoon, and you'll email it back just like just like the test, right? So it'll be similar to taking the test, and so and that will give you an opportunity to add points to your test number 2 score. So for some of you that could boost your score quite a bit. If you already have, however, a very high score, then there's no way to improve your score above 100. So if you already have, if you already scored in the 90s, then the makeup is not going to be very beneficial to you. I mean, you can take it if you like, but it won't add many points. Okay. So because you can't possibly score over 100 on test number 2, even with the additional points, right? It wouldn't boost you over 100. So if you're already in the 90s, it's not going to help you very much. But if you were in the 80s, it could help you, 70s for sure. But if you're lower than that, then definitely it could help you. But of course, you'll have to prepare, right, for the makeup. So you don't want to just download it and do it and turn it in, just thinking anything I can try here will help, because although I won't detract any points from your test number 2 score, you have to get at least 70% of the points on the makeup to get any benefit at all, right? So you understand that. So you can't just, just take the makeup on a lark and turn it in hoping for, just a few points here or there. It won't work like that. So if you don't get at least 70% on the makeup, you won't get anything added to your test number 2 score. Now, tomorrow, so Madison's schedule is a little bit different this week. Tomorrow at noon, Madison will have a session. And so instead of Thursday, it'll be tomorrow at noon. So you can ask questions about test number 2 of Madison. So you should really review your test number 2, and so that you can, maybe if you want to take the makeup, you can take the makeup, right? Okay. So again, that won't be till Thursday. So I'll mention this again on Thursday, but it won't be posted till after class on Thursday and then due on Friday. Do you have questions about that? Usually I get questions about this. So now a lot of y'all scored really high. So if you guys don't have questions, I understand, because there's really no benefit in for you in taking it. But otherwise, any questions about how the procedure is going to work there? Anybody who? Okay, all right. So I'm not gonna post this information. So this is privileged information. This is for people who are attending class, right? So I'm not gonna post it. We're gonna have a makeup. So it's just going to happen. So if you're not listening to me or I'm not paying attention in class, then you won't know about this, right? Okay, so you will miss this. So people who are not coming to class will have missed this opportunity. But that's just one of the advantages of coming to class, right? Okay, or at least watching the videos after class is over with. All right, so we have so if you have any questions about that, ask me. We have a homework that's due this evening, and I'm going to leave this one. So this is on evaluating limits. Now, we're really talking about this homework currently, the one that's due on Thursday. So probably this will get postponed, the due date, but I haven't changed it yet. But we're going to finish talking about this today. Okay, Calvin, did you have a question?
Yes. When did you say you were going to give us the makeup?
Yeah, so I'll post it on Thursday after class, right? So like we do the test, right? It'll show up on Blackboard, Thursday at 1:15, right? And then you would just work on it, and then you have to submit it by Friday, but I'm not sure the time yet. Sometime Friday afternoon. So it will be like questions from test number 2, but it's not going to be as long as test number 2. It'll be quite a bit shorter than test number 2. It'll be select problems, like problems from test number 2, and then so you will work those out, and just like test number 2, and then send them back to me, and then if you get at least 70% of the points on the makeup, then you will get points added to your test number 2 score. So I'll adjust your test number 2 score. Now, how I adjust your test number 2 score depends on how well you do on the makeup, but then also what your test number 2 score was. So if you scored very high on test number 2, you would get only a little, bit added to your test number 2 score. But if you scored, lower, then you could potentially add quite a few points to your test number 2 score. So that would, so that can, improve your average, right?
Okay, thank you.
Yeah. Now, okay. So on test number 2, one thing I did want to mention is, and I'm sorry I have to be so strict about this, but it's just the nature of the way we're taking tests. Is so you may have noticed that on your test I took off for not showing work, because I might have said no work shown, or I might have put question marks and then taken off points. That also means I don't understand what you did, the steps you did in a particular problem. And so so on the makeup, then try to, if I counted off for not showing your work in particular places, then try to make sure on the makeup, then you show your work, because I will count off again on the makeup just the same as on the test, right? Okay. Now I know some people, I can tell some people are putting down work that they did not do. Okay, so I can see that. All right, and so if you know, if again, if you don't have the correct work or enough work to justify the results that you got, then you're going to get points counted off, right? Okay, so you know, I can very clearly see when an answer was not something generated through the knowledge that you acquired in class, but was something that I think was generated by a calculator or by someone telling you. Okay, so you know, make sure that on the makeup, and then on your third test, on your final, right, make sure you're doing your own work, right? Okay, so I saw that in a few instances. Just don't do that. Okay, other questions about the makeup? Okay, let's see. Well, so most people around. So if you if you're just logging on, then you know, you missed some important information there. So you need to go back and look at the tape at the first part of this tape, right? Once I post it, to make sure you've you know, you heard what you needed to hear. But this homework is still due this evening, and then so finish that and then start working on this one, and then on Thursday we'll see when we actually want to make this one due. Okay, I hope we'll finish the notes on this one today, and then we'll see when would be appropriate time to make it due. Okay, other questions on anything? I have not added your participation scores yet, so I'll put that in at some point, but I haven't added that part. Okay, so that will also change your grade a little bit once I put in that participation score. Okay. All right. So well, and so if you don't have any questions for me, then I'm going to go ahead and start the lecture. So again, remember, Madison tomorrow at noon, right? It's Madison's time. So there's your chance to ask questions about you know, particular problems on test number 2, right? But the answer sheet is posted, so you can see the solutions. But if you don't understand the solutions, then you know, then talk to Madison. But I think it would help you to log on to Madison anyway, even if you don't have questions, so that you can see other people's questions or the things that Madison may want to point out about test number 2. She may have some insights into, you know, which problems need to be reviewed. Okay, I suspect she does, just from her experience as a student. Okay. All right. So I'm gonna go ahead and start talking here. Oh, but I do want to, for those people who scored on the 90s, those people who scored very high, I want to say that, you know, that was really, that's very excellent. All right. So if you're one of those people that made in the 90s, then, you know, that's great. Okay. You're doing very well. So you want to keep up that, whatever you're doing. So you can, you're well positioned to make an A in the class, and it's not a trivial achievement to make an A in calculus, right? Okay, that's an achievement, so you should feel proud about that. Okay, well, let me look at the notes then, and so we've been talking about finding turning points, right? Local extrema. Today we're going to also throw in inflection points, because the process is quite similar to finding turning points. Finding inflection points is really a very similar process. But last time we just talked about how to find possible turning points, okay? But we didn't actually go through the process of determining whether a possible turning point, a candidate for a turning point, actually turns out to be an authentic turning point on the graph. We looked at we found possible turning points, and then we looked at the graphs of the functions, and we could tell from the graph whether whether, you know, a candidate turning point really turned out to be an actual turning point, but we didn't talk about how to do that analytically without looking at the graph. So today we're going to finish that process, and we're going to learn how to figure out if possible turning points are actually truly turning points without having to look at the graph. But we will look at graphs as well, because it's really helpful to look at graphs. And the way to do this is really straightforward. It's exactly kind of what you would expect to do. So it's nothing that we're going to do today is going to be, really all that surprising. All right. Now it may be sometimes challenging because of the algebra, but the logic behind it will be very clear. Okay, so what's written here in the notes is what I just sort of said, right? Last time we learned how to find a possible extrema, possible turning points, and today we're going to see how to use the first derivative, of course, to figure out if those possible turning points really actually are turning points. All right, and this process is called the first derivative test. It's really not a test. It's kind of a like I said, it's kind of a process that you go through. Okay, and that's summarized here in this box in the notes, but I'm not going to read through this box because this is all stated very abstractly and doesn't make much sense until you actually see an example. But then when you see an example, it becomes really quite clear. Okay, so I'm going to jump immediately to an example of using, again, what's called the first derivative test, but it's actually kind of a series of steps. More than well, I guess it is a test, but you'll see what I mean here when we look at this very first example. Okay, so here we have a function, kind of a pretty standard function. This is a polynomial function because it just involves x raised to positive whole number powers. So whenever you have a formula where the parts of the formula, the terms of the formula are just powers of x like this, it's got to be positive whole number powers of x, though. You could have x to the 1/2 or x to the -1. But if you have that restriction, then that's a polynomial. So this is an example of a polynomial function, and that's about the easiest sort of function that one can work with. So this is a pretty straightforward example of what I'm getting ready to show you. And so what we want to figure out here, what we want to do here is locate where the possible turning points are on this function. So if we were to make a graph, but we're not going to make the graph first, we're going to go through the process first, and then we'll look at the graph later. But if we were to make a graph, where would the turning points be, right? Where would the local maxima be? Where would the local minima be? Okay, and furthermore, we want to decide when we find the possible turning points, is it an authentic turning point, right? Is it just something that could possibly be a turning point? Does it actually really in fact turn out to be a turning point? And what kind of turning point is it? Is it a local maximum? Is it a peak turning point, or is it a local minimum? Is it a trough or a valley turning point? Okay, so we want to learn how to figure all that out with pencil and paper without actually having to cheat and look at the graph. But we will look at the graph after we've decided on our answers here, just to verify sort of that we were correct. All right. So we already learned last time, right? We know how to look for possible turning points. Because those always exist where you have what are known as critical values or critical numbers. And remember, critical numbers are places where the first derivative is 0 or where the first derivative is undefined. Okay, so the first step in this so-called first derivative test, the first step in locating peak turning points and valley turning points is finding the so-called critical numbers where the first derivative is 0 or undefined, and that means you have to calculate the first derivative, right? So the first step of this process is exactly what you'd expect, right? We have to find the first derivative, right? So let's calculate f prime of x, and I think most of y'all did this really easily on the test for a function like this. This is going to be 3/2 times x squared, right? Minus, bring the 2 down, so we have 2 times 3/2 and then times x to the first power, right? Because we're going to subtract 1 from the 2. Fortunately, the 2's here cancel. So we get a really nice looking derivative there, right? It's going to be 3x squared minus 3x, right? So there's the first derivative. And then how do we find the critical numbers? So what do we do with the first derivative? Someone?
Set it equal to 0?
Yeah, set it equal to 0. It's what you almost always do with first derivative, right? You set it to 0, okay? So you're trying to find out where the first derivative is 0 or where the first derivative is undefined. Yeah, Melissa answered too. Sometimes I'm not reading the chats quickly enough, but Melissa also said set it to 0, which is correct, right, Melissa? Now, remember, you can also have, though, a critical number where the first derivative is undefined, not just where it's 0, but where it's undefined. But this first derivative is also a polynomial function. This is a nice, easy quadratic function because you have x squared here, right? And the domain of polynomial functions is all real numbers. So you can plug any number in for x into this formula. So you don't have any place where the first derivative is undefined. So don't have to worry about that. We just have to solve this equation. And that equation we can solve pretty easily by factoring. So you can factor out a 3x. So y'all are pretty good at solving quadratic equations on the test. So I was pleased by that because sometimes that's a real challenge for students. I don't know why, because I know you've done it lots of times already, but y'all did that pretty good. So we can factor out a 3x here from both terms. And so we get 3x times x minus 1 equals 0. And now it's pretty easy to see then that either x is 0, because 3x might be 0, right? That means x is 0, or x minus 1 might be 0, which means x is equal to 1. So you've got two critical numbers there. These are the critical numbers, x equals 0 and x equals 1. So so we might have a turning point at x equals 0, but maybe not, okay? Because critical numbers are where turning points can occur, but you don't have to have a turning point at a critical number. And then we may have a critical number at x. We may have a turning point at x equals 1, right? But again, maybe not. So how do we verify, in fact, that we do have a turning point at x equals 0, and or we do have a turning point at x equals 1, and even better, what kind of turning point is that? Is that going to be a peak turning point? So is the graph going to reach a local maximum at one of these critical numbers, or is it going to be a trough turning point or a valley turning point? Are we going to have a local minimum at one of these critical numbers? All right. So here's what we do now. Okay. We're kind of going to make a here a little very rough sketch of the graph. That's what I'm going to do. So, but very, very rough, okay, sketch of the graph. So I've drawn an x-axis here. I'm not even going to draw a y-axis. That's how rough our sketch is going to be, okay? And what I'm going to do is on the x-axis, let's go ahead and put in the critical numbers. So, but again, this is not going to be drawn to scale. This is all going to be just very rough, okay? So, I'm going to mark here 0 because that's one of my critical numbers. Then over here, I'm going to mark 1. Okay. So let me extend my x-axis a little bit. All right. So, this is a polynomial function, right? So, probably this polynomial function is rising and falling, correct? Polynomial functions have lots of wiggles in them when we graph them, right? Okay. So, around these critical numbers, the graph is, it's increasing and it's decreasing, right? But what I'd like to figure out is exactly where it's increasing and exactly where it's decreasing, because that's going to give me the information I need to decide if these critical numbers really are turning points and what kind of turning point we have, right? So here's what I'm going to do. I'm going to pick a number a little bit to the left of 0. Now, actually, so here on this side of 0, okay? Now, actually, you can pick as far to the left of 0 as you want to. So if you want to, you could pick all the way down here at x equals minus 1 million if you want, okay? But that's a little bit, you know, unnecessary. Pick a convenient value that's a little bit to the left of 0, a little bit less than 0, okay? So Alva, let me ask you, what do you think is a convenient number here that's less than 0? What's the first number you think of that's less than 0?
-1.
Yeah, that's what. Sure, right. Okay, that's what I would think too, right? So, so I'm just let's just mark that off on the x-axis. And again, Alva, you don't have to kind of draw this very accurately, right? So, you know, you don't have to get this spaced out perfectly or anything like that. So I'm just going to mark off -1 here on the x-axis. Now, Alva, what I want to know is at -1, if I were to graph, not the derivative, okay, but if I were to graph the original function, I've got it kind of obscured here, but here's the original function, x cubed minus 3/2 x squared. If I were to graph that, what I want to know is that graph going up or is that graph going down at -1? Is the graph increasing or is the graph decreasing at -1? What gives you that information if you can't really see the graph, right? So, you know, one way would be to make the graph and look, right? But if you can't actually draw the graph perfectly and look, how do you determine whether the graph is increasing or decreasing at -1? What gives you that information?
In the beginning of the equation, if it's a positive or negative.
At the beginning of the equation, you mean if this is a positive or a negative?
Yeah, in front of the x cubed.
That will tell you if the original function is above the x-axis or below the x-axis. So you have the right idea, okay? But I don't want to know if the graph is above the x-axis or below the x-axis. I don't want to know if the graph is positive or negative. What I want to know is the graph going up, right? Or is the graph going down? So you see, it could still be, it could be above the x-axis going up or down, or it could be below the x-axis also going up or down. I don't really care if it's above the x-axis or below the x-axis. I just want to know, is it rising or is it falling? So is it increasing or is it decreasing? So, so what function in calculus, what do you use to decide if a function is increasing or decreasing?
Something with the slope.
Increasing or decreasing is a rate of change. What tells us rate of change, Alba?
A derivative?
The derivative, right. You use the derivative. Yeah, it's the derivative that gives you information about increasing or decreasing. So what we're going to do is take the, let me do it down here. We're going to take the -1, not the 0. We're going to take the -1 and we're going to plug that into the derivative. Okay, so I'm going to calculate f prime of -1. So here's my formula for the derivative. So we got to remember that. But there's the formula for the derivative. So you get 3 times -1 squared minus 3 times a -1. And actually, Alva, you really don't care what this number turns out to be, but we might as well go ahead and calculate it. So we get what this is, -1 squared is 1 times 3, and this is -3 times -1, which is also +3. So it looks like we get 3 plus 3 here, which is 6. You can check me to see if that's correct, but I think that's correct. And I really don't care about the number 6. What I care about is that it's positive. 6 is a positive number, Alva. So that tells me the graph is going which direction at -1?
Up.
Up, right. So we're going to make a really ugly sketch of this, okay? I'm just going to draw a curve here that's going up. I could draw it as a straight line, but which is fine. But let me draw it with a little bit of curvature. I'm going to draw it like this, okay? Now, actually, it could be curved like this, okay? But or it could be a straight line, maybe. I don't think it's a straight line, though, right? Because that's not a formula for a straight line. So I'm really not sure how the curvature is supposed to look, but that's kind of irrelevant. So let me draw this curvature. By the way, what is that curvature called? That's concavity, right? Is that I drew it as concave what?
Concave down.
Yeah, concave down, right? But maybe it was wrong. Maybe it was really supposed to be concave up, but that's not important, all right? Now, so I know that over here at -1, the curve is going up. So see, this is a really vague sketch, right? Now, we're going to do the same thing between the two critical numbers. So between 0 and 1. And I think the obvious choice there would be 1/2. But you can pick any number between 0 and 1. So it doesn't have to be 1/2. That just seems like a convenient choice, okay? And then you're going to calculate f prime of 1/2 because you want to know, again, is the graph going up or down at 1/2? So now this one's not so, the arithmetic's not so easy here, right? So I have 3 times 1/2 squared minus 3 times 1/2. Let's see. So that looks like 1/2 squared is 1/4 times 3 is 3/4 minus, and this is 3/2 minus 3 times 1/2 is minus 3/2, right? So that comes out to be minus 3/4 if I did that right. And again, the number itself is not that meaningful to me. I don't really care what the size of this number is. What's important to me is it's negative. It's negative. Negative 3/4 is a negative number, right? So that means between 0 and 1, this curve is going down. Okay, between 0 and 1, the curve is going down. So guess what must have happened at 0? What did we get at 0? See, here it's going up and here it's going down. So what happened at 0?
We got an asymptote.
Not an
no.
asymptote, but a what?
A change in direction.
A change in direction. Yeah, we had a change in direction. And when you have a change in direction at a particular place, that place is called a what? We have several names for it in the class, but begins with a T.
A turning point.
Turning point, right? Yeah, you had to have a turning point here. So let me see if I can connect these two pieces. Let me see if I can connect these two pieces. I didn't connect them very well. All right. It looks like the turning point's right there, but it's not. It's right here at 0. Okay. This side was going up, right? This part of the curve is going up. This part of the curve is going down. And since these two pieces have to be, these two parts of the curve have to be connected, that means we have to have a turning point right here, right? Okay, so there is a turning point at x equals 0, and in fact, it is a peak turning point. So you have here a local maximum, okay? That's it. That's just all the logic you use to determine if, you know, if that critical number really is a turning point, okay? Oh, Melissa, you don't understand how it's a turning point? Oh, you don't, or now you do? You said yes. I don't know what. I'm not sure what question you're answering with the yes. You don't know how it's a turning point?
Confirming that she doesn't understand.
Okay. Yeah, that's right. We just plugged in numbers. That's right. Okay. So we use the derivative there, okay, right, to figure out where the curve is increasing and where it's decreasing. So we know at -1, because the derivative is positive, 6 is a positive number, right? We know the curve here is going up. So over here to the left of 0, the curve is going up. To the right of 0, by using 1/2, we plugged 1/2 into the derivative. We got negative 3/4. That's less than 0. That means at 1/2, the curve is going down. Okay, well, if you're switching from going up to going down, that means you must have peaked out somewhere, right? Okay, so right here at 0, we must have a turning point, okay? All right, because we went from going up to going down. And this is, in fact, a peak turning point. So we know that at x equals 0, we have a local maximum. I don't exactly know. Now we can figure out actually the coordinates of this turning point. We know the x coordinate is 0, and then you can find the y coordinate by plugging it into the formula. Don't plug it into the derivative, but plug it into the original formula. Oh, that turns out to be 0. So this point actually is 0, 0. That's why I said this is a really rough sketch, right? Okay, that doesn't look like it should be 0, 0, but in fact it is, all right, in reality. All right, now we have to figure out the same thing for 1. Is that that looks like that's going to be a valley turning point, right? Because I have a feeling this graph is going to switch over from decreasing to increasing, but let's see if that really happens. So again, you pick a number a little bit bigger than 1, and 2 would be a convenient choice, but you can pick any number bigger than 1 that you like. It doesn't really matter. And then you're going to calculate the derivative at that number. So let's calculate f prime of 2. So we get 3 times 2 squared minus 3 times 2. And let's see, that's going to be pretty big, I think. So you get 3 times 4, which is 12, minus 6, which, oh, that's 6 again, which is positive. The 6 itself is kind of meaningless to me, but the fact that it's positive means that, see, over here at 2, the graph is going up again. It's increasing. I drew it as concave up, but maybe it was concave down. And that means that at 1, we must, to connect these two pieces together, the decreasing and the increasing piece, right? We have to do that with a turning point. So at 1, we have a turning point, and it's a valley turning point, right? It's a local minimum because the curve is switching from decreasing to increasing. Where it switches from decreasing to increasing, that means you have a local minimum. All right, so what is that actual turning point? Just take the 1 and plug it into the formula, and you get 1 minus 3/2. So it turns out that this is 1 and minus 1/2. That is the second turning point. So altogether, what did we discover here? Well, we discovered we've got, 2 turning points, right? We have a local maximum at 0, 0, a peak turning point at 0, 0. We have a local minimum at 1 minus 1/2, a valley turning point at 1 minus 1/2. We also know something else. We know now where the curve is increasing and where it's decreasing. So let me write that down. It's increasing. Where's that thing increasing? From negative infinity, this part is increasing, right? So it's increasing from negative infinity to 0. And then it's increasing again from 1 to infinity. And then the only place it's decreasing is between the 2 turning points. So that would be 0 to 1 is where it's decreasing. So we really know, short of drawing the graph, we really know everything there is to know about this function. Well, not everything, but we know a lot about the function, right? We know where it's increasing, we know where it's decreasing, and we know where the 2 turning points. I guess the only thing we don't know yet is the concavity. So we're really not sure if in this rough sketch of the graph, if I drew this properly, okay? But so we're really not sure if I've got the concavity right yet, okay? That's yet to be discovered. Let's draw a, let's look at a graph of this. So I have a graph of this, and already drawn, and there's the graph, okay? It's not actually that bad, right? The graph that I drew, that rough sketch that I drew actually is not that bad. There's the actual curve there. So you see you have that peak turning point at 0, 0. And then it dips down here to, this is 1 and minus 1/2. Okay, looks like we have a couple of x-intercepts, which we didn't find. We have an x-intercept at 0, and we have an x-intercept at 1 point. Is that 1.5? Yeah, we have an x-intercept at 3/2, 1.5. We didn't look for the x-intercepts, but that's not really a calculus question, right? That's an algebra question. Okay. All right. Well, so that is the so-called first derivative test, right? That we're just kind of using the first derivative over and over again there, right? To find the possible turning points, and then to verify if those possible turning points really do turn out to be actual turning points. And sometimes they do not, okay? So you can get fooled, all right? There are instances where a critical number does not result in a turning point. Okay, so let's see. To find, what was your question here? To find -1/2 for the coordinate, we plugged 1 into, yes, into the original equation, right? Don't, when you're looking for coordinates on the curve, don't plug into the derivative, right? Okay, plug into the original function. Okay, now this one's going to be a little bit tougher now because it involves a trig function, right? Okay, so that's going to make it a little bit harder, but let's go through the steps here again. All right, so what we're trying to find for this function, and then we'll take a look at a graph of this. So what we're trying to find for this function is, does it have any turning points? I'm certain that it will, because the sine curve, right, is wavy, right? It's called the sine wave. This is not just the sine curve by itself because we have this extra term, but that's almost certainly going to make it have that sine x is almost certainly making this curve have lots of waves in it. They got lots of waves in it. That means it's going to have lots of turning points, right? So, so almost certainly we'll have some turning points here. So we're trying to figure out, where are those turning points, and are they peak turning points, or are they valley turning points? Are they local maxima, or are they local minima? Now, the domain of this function is all real numbers, because you can plug x in and multiply by 1/2, right? Any value for x, and you can calculate the sine of any number. So we can plug any value for x in here. So that means the domain of this function is all real numbers. So this curve extends all the way across the x-axis from -infinity to +infinity. And again, because it's got this sine x as in the formula, that means it's probably got lots of, it's very wavy probably, which means it has lots of turning points. So we're going to have to make this problem a little bit more tractable, we're going to have to restrict the domain here. So we're only interested in turning points from 0 to 2 pi, okay? That's the only part of the curve that we're interested in here. All right, so we don't have to make this restriction, but we're doing it just to make the problem a little bit easier to handle. All right, so let's see if we can go through this process, right? What is the first step? So in calculus, it's the first step is kind of always the same, but what do we do first?
Finding the derivative?
Yeah, sure, find the derivative, right? Yeah, we're not gonna be able to get anywhere at all without finding the derivative correct, right? So that's the first thing, right? So let's see if we can write down the derivative here. So we have f prime of x is equal to, well, that's easy. So everyone would have got this right on the test. The derivative of 1/2 x is 1/2, right? And the derivative of sine x is cosine. So there's an easy derivative to calculate, right? And now we want to find the critical numbers by setting this to 0. And now we have a little bit trickier equation to solve. 1/2 minus cosine of x is equal to 0. So I'm going to bring the cosine x over to the right-hand side. So I get cosine of x is equal to 1/2. And now we have to solve this one by inspection. I just got to think about where is the cosine 1/2, right? Remember, we're thinking in radians, not in degrees. So don't think in degrees here, right? So I have to remember where is the cosine 1/2 so I can solve this equation. And remember, I want all possible values for x between 0 and 2 pi. So don't stop when you just find the first answer, right? You've got to find all values for x from 0 to 2 pi. So I've drawn a little a set of axes here so we can draw some angles, right? Because x is going to, we want to think of x as an angle, right? So we can remember what angles have cosine 1/2. What's the first candidate in the first quadrant? What angle has cosine 1/2? That's the first thing you would look for. So can y'all remember that? Remember, cosine starts at cosine of 0 is 0, right? Cosine of 0 is 0, and then when you go up to pi over 2, when you open an angle to pi over 2, that's 90 degrees, right? Cosine goes up to 1, okay? I said it backwards there, didn't I? So I'm sorry. Cosine of 0 is 1, and cosine of pi over 2 is 0. Okay, so
Is pi over 3.
pi over 3, right, man? That's good. You remembered it.
And then 5 pi over 3.
Right. Pi over 3 is that angle in the first quadrant that has cosine 1/2, right? Okay. So pi over 3 is 60 degrees, right? So so we know that x can be pi over 3, right? So because cosine of pi over 3 is 1/2. All right. Now, but we're looking for all possibilities between 0 and 2 pi, right? So, but we want cosine to be positive, not negative. And remember, cosine is positive where the x-axis is positive, right? So we need an angle in the first quadrant, which we already found, pi over 3, or we need an angle in the fourth quadrant, right? And we need the angle in the fourth quadrant whose reference angle is pi over 3. So we want an angle such that the reference angle here would be pi over 3. Okay. Well, what angle is that? Well, to get to this angle, right, from this initial side along the x-axis, we would have to rotate how far? That would be 5 pi over 3, right? Because if you rotate 5 pi over 3, then you would have pi over 3 left to get to one full rotation. So 5 pi over 3 has a reference angle of pi over 3. So that means the cosine of 5 pi over 3 is going to be the same as the cosine of pi over 3, but we already know that's 1/2. So our two values there for x are the easy one, pi over 3, and the one over here in the fourth quadrant is 5 pi over 3. Okay. That's it, because any angles here in the second and third quadrant, right, they will have negative cosine, but we want cosine to be positive 1/2. Okay, all right, so so we located these two values. These are critical, right? Remember, these are called the critical numbers. So we found the critical numbers, right? And now we just have to figure out, wow, are those critical numbers really going to be, are they really going to correspond to turning points? Are they just kind of fake critical numbers, right? Are they just imaginary turning points on the graph of this curve? All right, so let's mark those off. So I've drawn here my tiny little x-axis here, right, where I'm going to make a really ugly curve of this, a really ugly graph of this curve. So let's just mark off pi over 3 and 5 pi over 3, right? And now you want to pick some values to the left and right, of pi over 3 and 5 pi over 3, because you're trying to determine what is the how is the curve increasing or decreasing around these critical numbers, right? Around these possible turning points. Okay. All right. So who wants to start for me there? Just let's go from left to right. So let's pick something that's to the left of pi over 3. Make sure you pick something easy. Okay. All right. So what's an easy value to the left of pi over 3? Someone want to help me here? Pi over 8. Yeah, Melissa, pi over 8. Well, that is a little bit below pi over 3, but that's a really messy value. So, I mean, we could use it, right? Especially with a calculator. But Melissa, there's an obvious easy choice. That's no, pi over 2 is a little bit bigger than pi over 3. You're overlooking the easy one. What?
Pi
Yeah, no.
or 0?
0. There you go. Right. Okay. Yeah. So let's start with 0. All right. So, but really any value will do. So I when I'm holding out there for a different number, I'm just doing that for convenience. Pi over 8 would be fine. Okay. I mean, you could use pi over 8 as a test value. All right. It's just going to make you do a little bit more arithmetic. All right. But with a calculator, it's not bad. All right. But 0 is really easy to work with, right? So what we need to do is calculate f prime of 0, right? Okay. And so that's 1/2. Remember, not the original function yet. Okay. Use the derivative. So you have 1/2 minus the cosine of 0. But we already talked about cosine of 0 is 1, right? So we have 1/2 minus 1, which is minus 1/2. And I really don't care that it's minus 1/2. I just care that it's minus, right? Minus 1/2 is less than 0. And so that means this part of the curve is doing what? Over here to the left of pi over 3, the curve is going up or going down, increasing or decreasing?
Down.
Down, right? Okay. So so let's draw a little downward curve. Let me draw it like this. I'm drawing it as concave up, but maybe it's concave down, I don't know. All right. So or you could just draw it as a straight line. Okay, it's not a straight line, obviously, but we're just trying to make a really ugly sketch of a curve, right, that's going down. Now let's pick something between pi over 3 and 5 pi over 3. Right, so what's between pi over 3 and 5 pi over 3 that's really easy to work with? If you want to pick a whole number, that's fine, okay? But if you want to pick a radian value, that's fine too. See, here's pi over 3, right? And then there's 5 pi over 3 over there. So what's between pi over 3 and 5 pi over 3? If you're going around your, circle here. There's pi over 3. So if you're going from pi over 3 and you're going to 5 pi over 3, what nice values are you crossing over? What's this value?
1. Oh, no.
Now these are angles, right? So yeah. Yeah, see, as we're going up, when you hit this right there, what angle are you at?
I can't. 60.
No, pi over 3 is 60, but we went past pi over 3. We got up to vertical here.
90.
Yeah, that's 90, which in radians is what?
0 or 1.
No, in radians.
Pi over 2.
Pi over 2, right? Okay, so you could use pi over 2, for instance. See, that's bigger than pi over 3, but less than 5 pi over 3. But so pi over 2, what's down here? What about when you go half a revolution?
Pi.
Pi. That one's really easy to work with. So that would be the one I would pick, is pi. I'm not sure where to position that between pi over 3 and 5 pi over 3, but somewhere in between there is pi, right? Okay. And so let's calculate f prime of pi. So there's f prime, right? So we have 1/2 minus the cosine of pi, but what's the cosine of pi? Yeah, pi starts, cosine starts at 1, goes down to 0, and then when you get to pi, what's cosine? Did someone put it there? Oh yeah, y'all keep answering and I'm not paying attention. So yeah, it's -1. So cosine of pi is -1. So you get 1 minus a -1. So that's, I mean, you get 1/2 minus a -1. That's 1/2 plus 1. So that's 3/2, which is positive. Okay. So so the curve is switched to going up again, you see. Okay. So the curve is switched to going up between pi over 3 and 5 pi over 3. The curve is going up. So guess what we have right here at pi over 3? We do have a turning point because the curve is switching from decreasing to increasing. So what kind of turning point is that? It's the kind I've drawn, right? So What would y'all call that? Informally, I call that a valley turning point. What's the correct term for that kind of turning point? Yeah, I've drawn this whole piece as concave up, but the turning point, what kind of turning point is that? It's a valley turning point because you're going from decreasing to increasing. What's the technical term for a valley turning point? It's a local something.
Minimum?
Yeah, this is a local minimum. So we have a local minimum here at this turning point, which is pi over 3 and something. So what's the y coordinate? You find that by plugging it into the original function. Okay, that's a little bit harder to calculate. So you have 1/2 pi over 3 minus the sine of pi over 3. Okay, I'll let someone do that calculation for me. If you want to give it to me in decimal terms, that's fine. So while I'm continuing the problem here, someone calculate that for me. What is the y coordinate of this turning point when you plug pi over 3 into the original curve? All right. Now let's go to our second possible turning point here, which is at 5 pi over 3, right? Okay. So now we need to pick a value here that's a little bit bigger than 5 pi over 3. So what's a number here to the what's a number there to the right of 5 pi over 3? So what's a convenient number over here I can pick? See, there's 5 pi over 3. So if we go past 5 pi over 3, one revolution would be past 5 pi over 3, right? What's the value of one revolution?
2 pi.
2 pi. So we can pick over here 2 pi, right? Okay. As another test value. And then calculate f prime of 2 pi. Okay. So 2 pi is a little bit bigger than 5 pi over 3. Let's see what's happening to the curve at 2 pi. So we get 1/2 minus the cosine of 2 pi. But what's the cosine of 2 pi? 2 pi is the same as 0, right? Because you've made one revolution. So what's the cosine of 2 pi? Same as cosine of 0. What's cosine of 0? We mentioned that a moment ago. What? 1? Yeah. Okay. So we get 1/2 minus 1, which is minus 1/2 again. So kind of what we expected. That's less than 0. So over here, the curve is decreasing again, right? So it looks like we've switched from increasing. This part is decreasing. So that had to happen. The only way to connect those two parts of the curve is with a turning point, right? Okay. So it looks like we have a peak turning point at 5 pi over 3. Okay. So a peak turning point is a local maximum at 5 pi over 3. And I wonder what the y coordinate is. Well, you get that by plugging that into your original function. So what y'all get for the y coordinate here? Minus, is that it? Minus 0.3424? Is that the one? Minus 0.3424? Minus 0.3424. And what about there? Can someone do that math for me? Plug the 5 pi over 3 into the original function. So you would have 1/2 times 5 pi over 3 minus the sine of 5 pi over 3, whatever that is. Okay. And then simplify and see what value we get there. Okay. And you plug that in. Make sure you can do something like that on a calculator, right? Okay. Make sure you're in radian mode, right? So you can plug these radian values right into this original function, so you can get a decimal approximation for the y coordinate. So I have a local minimum here. Here I have a local maximum, right? Okay. Let's see. Where's the function increasing? It looks like it's increasing between pi over 3 and 5 pi over 3, right? pi over 3 and 5 pi over 3. And then where's it decreasing? Remember, I'm only interested in 0 to 2 pi. So it looks like it's decreasing from 0 to pi over 3, 0 to pi over 3, and then increasing again from 5 pi over 3 up to 2 pi. Don't go to infinity, right? Because we were only interested in the part of the x-axis from 0 to 2 pi. Let's take a look at the graph and see if is it possible I got this right? I don't know. Let's see. So let me see if I can open this one. If I can remember which example this is. I think it's this one. Yeah. All right. So I got that one right. Whoops. All right. So there's the curve between there's the curve from just from 0 up to 2 pi is about right here. So indeed, we have this local minimum right there. Oh, y'all calculated that beautifully for me. Minus 0.342, right? Yeah, that's what Desmos agrees with right there at pi over 3 and minus 0.342. There's our local minimum, and then another one up here at 5 pi over 3. Did y'all get that one right? Oh, you did. 3.484. Okay, so there's the y coordinate when you plug the 5 pi over 3 into the
Professor, are you on mute? I can't hear you.
Oh, am I on? Oh, what did I do?
I can hear you.
I can hear you.
Oh, okay. Let me turn my participants back on here and see. Let's see. Am I? Yeah, okay. The microphone shows it's working, so I think I'm on. Okay, so there is the yeah, so there's our second turning point right there, a local maximum at 5 pi over 3, and then at 3.484, which someone calculated there for me beautifully, right? Okay. Great. All right. So see, that's kind of it's a little bit of a process, right? So it takes a few steps, but then that gives you really, just with pencil and paper, right? You have a really good idea even before you make the graph, right, of what you can expect, right, when you graph one of these. When you graph a function, right? Now, what we didn't quite know yet was about the concavity. And the concavity of this curve is changing right here. It's concave up, and then it's going to switch here to this part is concave down, right? So, so that's one mystery that we haven't quite solved yet, right? It's how to figure out, where the concavity is changing from up and down, and then where the inflection points are. There's going to be an inflection point on this curve, maybe about right here, because it looks like right about there, it's switching from concave up to concave down, but we haven't learned how to do that yet. Okay. All right. So, so that part, we're not quite skilled at, but it turns out that's pretty easy. Okay. Very similar to this first derivative process that we've been going through. Okay, so all right, so let's pause right there for a few minutes, and we've got a couple more examples to look at, and going through this process, right? But let's take a little bit of a break here to maybe about 12:45, right? So I'm going to pause the recording, and then we'll come back at about 12:45 and look at some other examples. Okay. Okay, so let's resume here, and let's try at least one more. I've got some more examples, but let's try at least one more. I'm not sure how much time we've got how much more time we'll have for examples, but let's look at this one, which is just a little quirky because it involves this exponent of 2/3, right? Which remember that's going to involve a cube root, correct? At some point, but I'm not sure we actually have to think about cube roots or not. But a third exponent, right, indicates cube root. Okay, so again, we want to see if we can locate the turning points here on this particular graph, right? So just like before, right, the process is the same. You've got to start with derivative, right? So let's take the first derivative. This one is a little bit more complicated, the derivative, than the first two, but not much worse, right? You're going to bring the 2/3 down, correct, right? So you're going to use the power rule times x squared minus 4 to the 2/3 minus 1. So that's going to give us ultimately a negative 1/3 exponent, right? But then remember, the chain rule is going to come into play here too. So y'all did very good with the chain rule also on the test. Y'all weren't forgetting that. So because this is an expression raised to a power, not just x raised to this power, right? We have to finish off our derivative by multiplying in the derivative of x squared minus 4. But that's a pretty easy derivative, right? That's just going to be 2x. So now let's see if we can simplify this kind of ugly derivative expression a little bit before we start using it. So let's take the 2x and multiply it by the 2/3. So that's going to be 4x over 3, right? 2 times 2x is 4x. And then you still have the 3 in the denominator. And then, of course, the 2/3 minus 1 exponent, that's going to be negative 1/3, right? And let's make that a positive exponent by bringing that to the denominator. So it looks like we have 4x over 3 times x squared minus 4 to the 1/3 power. And now I am going to write that 1/3 power as a cube root. 1/3 power means cube root. So let's write that as a cube root because I think that'd be easier for us to work with. So we have 4 over 3 times the cube root of x squared minus 4. Okay. And now let's see if we can figure out the critical numbers. All right. Well, okay. So the critical numbers in this one are going to be a little bit trickier to find, but you'll start off finding the critical numbers, you know, in always the same way. Set the derivative first to 0, right? So set the derivative to 0 and try to solve that equation. Now, y'all did this very nicely on the test as well, right? When I set this derivative to 0 and try to solve this equation for 0, what am I immediately going to assume then? Or what am I immediately going to do? So you've got that fraction equals 0. When do fractions equal 0?
When x equals 0? No.
Yeah, when x equals 0. Why? But why do you know that? So x equals 0 is the solution, but why do you know x equals 0 is the solution? Was that
Anything divided by, anything divided by 0 is 0, or either that or it cancels out.
Well, when you have a fraction, Alba, that equals 0, what do you know about the fraction? When you have any sort of fraction that equals 0, the only way that can happen is if what is true?
If the denominator is 0?
Not the denominator. You got it back.
The numerator.
The what?
The numerator.
The numerator, right? Yeah. When a fraction is equal to 0, the only way that can happen is if the numerator is 0. The bottom cannot be 0, right? Because then you would have undefined, correct? So the only way a fraction can equal 0 is if the top is equal to 0. So we know here that we can just discard the denominator, right? And then we know that 4x has to be 0 which you were correct. X has to be 0. So one of our critical numbers is x equals 0. So let's mark that off on our little, scratch x-axis here, right? Okay, so there's one of our critical numbers. But Alva, in this one, we have a couple of other critical numbers because it's also possible to get critical numbers where your derivative is not defined. And your derivative is not going to be defined here where the denominator is 0. Okay, so now we have to think about where is this denominator possibly equal to 0? Okay, well, of course, 3 is not equal to 0, so that you can sort of ignore that. But it is possible for this cube root to be 0 because the cube root of 0 is 0. So if this quantity under the cube root turns out to be 0, then you're going to get undefined. Okay, and so we have another possible critical numbers where the x squared minus 4 is 0. So let's write that down. X squared minus 4 equals 0 also may give us critical numbers. That's not the solutions to the equation, but that's what makes the fraction undefined, and that's what makes the first derivative undefined, and that gives us critical numbers. So so we have to solve this equation as well. X squared minus 4 equals 0. That's pretty obvious. That means that x squared is equal to 4, and you can just solve that one by inspection. If x squared is equal to 4, then what is x got to be equal to?
2
That's one possibility. There's one more.
or -2.
-2, right? Yeah, don't forget the -2. Okay, so there are your other critical numbers. You have another critical number here at -2 and one over here at 2. So let me fill them in. All right, so we've got 3 possible turning points here. Oh, by the way, check these to make sure that they're in the domain of the original function, because if they're not in the domain of the original function, then you can throw them out, okay? But if you plug 2 in here, that's okay. You'll get 2 squared minus 4 is 0 to the 2/3 power is 0. So that is part of the domain of the original function, and same thing with -2. So these are in the domain of the original function, so they may be turning points, okay? So we end up with a lot of possible turning points here. One at -2, one at 0, and one at 2. So we got to check them all. So here you got a lot of work to do. So pick a number here less than -2. Start there, less than -2. What's an obvious choice?
-3.
Yeah, I'd pick -3. And you have to plug that into the derivative, okay? And look at the sign. Ooh, okay. So let's see what happens when we plug that into the derivative. So we have f prime of -3. So it's going to be 4 times -3 over 3 times the cube root of, this is the cube root of -3 squared minus 4. Well, look, now, so if you want to, you can do these calculations, but you can figure out what you need without really doing the calculations. Look, -3 squared is +9. So you have 9 minus 4, which is 5. So cube root of 5 is positive. 3 is positive. So you end up in the denominator with a positive number. I don't know exactly what it is, but it's positive. But 4 times -3 is a negative number in the numerator. So we have minus divided by plus. What is that sign?
Positive.
What's
Oh.
no, yeah, minus divided by plus.
Oh,
What sign do
negative.
you get? What?
Negative.
Negative. So this is less than 0. I don't care exactly what it is, what the value is, okay? It's less than 0. So that means this part of the curve is going down, okay? Over here, it's going down. All right, now let's pick something between 0 and -2. Oops, I think it's -1 would be the obvious choice there, right? Okay, so do I have room here? F prime of -1. What's the derivative at -1? So you get 4 times -1 over 3 times the cube root of -1 squared minus 4. Wow. What's the sign going to be there? Well, the top sign is negative. What about the bottom sign? Well, you have -1 squared. That's +1. -4 is -3. So you have the cube root of -3, which is negative, times +3 is negative. So the bottom ends up being minus. If y'all aren't comfortable now just looking at the signs, go ahead and do the calculations with your calculator. All right, it's not going to hurt to do the calculations with your calculator. You'll come up with a value here, right? What value you get is kind of irrelevant, but what's important is the sign. Minus over minus is plus, so you're going to get a positive number out of that. So this part of the curve between -2 and 0 is going up. So guess what happened at -2? You got a turning point, right? Because it switched from decreasing to increasing. So there we have a turning point. Now, you want to go through the same analysis, pick a number between 0 and 2. The obvious choice is 1, and then pick a number bigger than 2. Obvious choice there again would be 3. Okay. I think what happens there is you end up with this part of the curve going down and this part of the curve going up. I think the first derivative has a negative sign here at 1, and the first derivative has a positive sign here at 3. So we end up with going down and coming up, which means, let's see, we have a turning point here at 2, and also we have a turning point at 0. Well, I wonder if that's correct. So it looks like we get this very wiggly curve, right? Okay, with 3 turning points on it. One of them is at -2. And then another one here at 0. This is actually, oh, I don't know what that is. Okay. So another at 0, and then another here at 2. Okay. Is that going too fast, or have y'all tuned out? Don't tune out, because this is a good lengthy example. So it's got lots of good things to look at there, right? Okay. There's lots of arithmetic here when you're evaluating the derivative, but again, you can use your calculator, right? Okay, and all you're really interested in is the sign of the derivative, right, around these critical numbers. Okay, we want to know if the curve is increasing or decreasing around these critical numbers, so we can decide if these critical numbers really result in actual turning points. Okay. All right, so before we take a look at the actual graph, and let's see if my rough sketch there is sort of correct or not. Let's write down where the function is increasing. Okay, so someone help me there. Daniel, are you there? Can you tell me, just from looking at what we roughly sketched there, where the curve is increasing? Where on the x-axis the curve is increasing? So where is it going up there, Daniel?
From -2 to 0 is
Yeah.
increasing.
Yeah, -2 to 0, and again, it's going up from where?
From 2 to 3, or maybe it's continue.
Yeah, it's infinity, right? Yeah, because this curve really is extending, right? Okay, I only drew part of it. So it's increasing from -2 to 0 and 2 to infinity. And where is it decreasing? So what's the rest of it? From where?
Infinity to -2. Negative infinity to -2.
Yeah, negative infinity to -2, and then again from
0 to +2.
Yeah, 0 to 2, right? Yeah. Okay.
0 and positive.
Yeah, right there. Yeah, got it. So yeah, you said it exactly correct. So yeah, so that's where it's increasing and that's where it's decreasing, right? So let's see if let's see if I got that right. Somehow I'm not confident for some reason here. I keep wiping out my participants. So let's see. What example is it's this one? Oh, well, so yeah, so I know now why I wasn't confident there. Okay, so there's what the actual graph looks like. So it is decreasing and then increasing and then decreasing and then increasing. So we got the shape of the graph right, okay? But what did I get kind of wrong on the graph? See, there's what I drew as kind of, really a very rough sketch. But what's wrong with my graph and the actual correct graph?
There is a sharp turn and
Yeah, there are sharp turning points here. So these were sharp turning points, right? These were not smooth turning points like I drew them. And Daniel, what else is wrong? See, how did I draw this part of the curve I drew as what curvature?
concave up.
Yeah, concave up, but that's not how the graph was, right? This is concave down, and then this is concave down again, and then this is also concave down. So this thing is always concave down everywhere, right? See, that piece is concave down, that's concave down, that's concave down. So I completely blew the concavity, all right? Because I have it concave up and then concave down and then concave up again, right? Okay, so I didn't get the shape of the curve at all right. I got, where it was increasing and decreasing correct, but I totally missed the shape, right? So that brings up the question of, wow, how do I figure out concavity? Okay, so how do we determine, where is a graph concave up, where is it concave down, and where does that change? That is the inflection points, right, where it changes concavity. Now that's a less, kind of a less important question than where it's increasing and where it's decreasing. But still, that's something that we would like to be able to determine, okay, is the concavity. All right, so now I'm going to show you how to do that because it's exactly the same process, okay, well, with one slight difference, okay? So I had another example here, but we'll skip this example because I want to jump down exactly to this question. How do we determine where a function is concave up and where it's concave down, and where are the inflection points, okay? So how do I do that? And the answer is you go through exactly the same process as we did for determining, where it's increasing, where it's decreasing, and where the turning points are, except you use the second derivative. All right, so it's the second derivative that tells us about concavity. The first derivative tells us about direction, right? Increasing, decreasing. The second derivative tells us about curvature, concavity. But the process is identical, okay? So if you know how to figure out where a curve is increasing and decreasing and where the turning points are, or what the turning points are, then you know how to determine where a curve is concave up and concave down and where the inflection points are. All right, so let's go through this process. We have just time for one example, but the example will already feel really familiar to you. Okay, so we're going to try to figure out where the inflection points are on this curve, and then where the curve is concave up and where it's concave down. All right, and so we're going to go through exactly the same process, except we will use the second derivative, not the first derivative. Well, that means we have to calculate the second derivative, right? So let's see if we can calculate the second derivative here. Well, we got to calculate the first derivative first, right? So what is the first derivative of x to the fourth minus 4x cubed? What's the first derivative? Someone?
4x 3 square.
Right? And then what?
And minus 12x square.
Right, perfect, yeah. So there's the first derivative, Daniel. See how fast you are at that now? Right, so you're very good at that, right? So becoming a very skilled calculus practitioner now. Now, what's the second derivative?
12x square and negative 24x.
Perfect, right. And now we look for the possible inflection points. And you're going to have possible inflection points where the second derivative is 0 or where the second derivative is undefined. Just like with turning points occur where the first derivative is 0 or undefined, inflection points can occur, they don't have to occur, but can occur where the second derivative is 0 or undefined. Well, this second derivative is defined everywhere. Its domain is all x values. So you can plug any x number in here that you like. So undefined is not an issue, but the second derivative can be 0, and because we have solutions to this equation. So let's see what the solutions to this equation are. Factor out a 12x, and that would give you x minus 2. So Daniel, what are the two solutions to that equation then? (12x times x minus 2 equals 0).
1.
So it may be that 12x is 0, Daniel. So if 12x is 0, what's x? See, 12x might be 0, which means x is what?
0.
0. Or x minus 2 might be 0, which means x is what?
Positive 2.
Yeah, positive 2. Exactly. Right. Remember, this product is 0. That means one of the factors is 0. So either 12x is 0, which means x has to be 0, or x minus 2 is 0, which means x is 2. So Daniel, there are your two possible inflection points. One of them is at 0 and one of them is at 2. Okay. And now you do the same thing we did before. Pick a number a little bit less than 0. I would say minus 1. Pick a number, because that's a convenient choice. Pick a number between 0 and 2. If you don't pick 1, then you're a really strange person. So between 0 and 2, pick 1, and then a number a little bit bigger than 2, I would say 3. Okay, but doesn't have to be 3, right? And then plug those into, be careful, into the second derivative, and check the sign. So you're going through the same process as when we were checking turning points, but you use the second derivative. So plug the minus 1 into the second derivative and look at what the sign is. So you have 12 times minus 1 squared minus 24 times a minus 1. Let's see, what's that going to be? That's 12 plus 24. If I'm doing the signs right, yeah. Minus 1 squared is 1, times 12 is 12, minus 24 times minus 1 is plus 24. That's 36, which is positive. So at -1, that means the curve is concave up because this number is positive. So I'm going to draw a concave up here. All right, concave up. Now let's check at 1. So do f double prime of 1. So when you plug 1 in here, that's easy to plug 1 in. You get 12 times 1 squared minus 24 times 1. So you get 12 minus 24, which is negative 12, which is negative. So this part is concave down like this. So you went from concave up to concave down. So the concavity switched. So what happened right here at 0? What must be there? Where the concavity switches, what's that point called?
Inflection.
Inflection point, yes. So you have an inflection point at x equal 0. Not a turning point though, Lance, okay? So I don't know that the curve is turning over here, okay? All I know is that the concavity is switching, right? So at 0, you have a change in the concavity. Let's see, what's the y coordinate of that point? Make sure you go back to the original function. So if you plug 0 into the original function, that's easy, you get 0. So we have an inflection point at 0, 0. The concavity is going to switch at 0, 0. Now the other possible inflection point, where was that? 2, right? Right there. So let's check the second derivative at 3. So we'll calculate f double prime of 3. That's going to be I don't know what that number is. So we have 12 times 3 squared minus 24 times 3. So I'm going to have to do some arithmetic here. What's 9 times 12? I think that's 108, isn't it? Minus 3 times 24 is 72. So we get 36 again, which is positive. The 36 is kind of meaningless to me, but the fact that it's positive is what's important. So that means that over here at 3, we've gone what? Back to concave up? Back to concave up. So right there at 2, you're going to connect these two pieces of the curve. You have to connect them with an inflection point because they're switching from, the curve is switching from concave down to concave up. Let's see, what are the coordinates of that point? 2, and when you plug 2 into here, you get 16 minus 32. So that looks like negative 16 if I'm thinking correctly. Yeah, 2 to the 4th power 16 minus 4 times 2 cubed is 8. So minus 4 times 8 is 32. So you get negative 16. Let's, are we out of time? Oops. Yeah, just enough time to finish. Yeah, let's look at the graph. So let's look at that and see if in fact, we got the concavity correct. Let me see. I think that's this one. So did I do that right? So right there, see concave at 0, 0, concave up, then switch to concave down, right? So see, in fact, you do have an inflection point at 0, 0. Not a turning point though, right? Okay, that's not a turning point, but it is an inflection point. This part is concave up, this part is concave down. And then you have another inflection point here at 2, and this is minus 16. 2 and minus 16 is, I didn't point very, yeah, there it is. At 2 and minus 16, there is the other inflection point because we switched from concave down back to this part of the curve is concave up. We didn't bother to find this turning point, but there was a turning point at 3 and minus 27. We could have found that though with the first derivative test, right? Okay. I bet we would have thought that 0, 0 was a turning point. So that would have been a critical number at 0, but it would have been a critical number that turned out to not be a turning point, okay? Remember, not all critical numbers are actual turning points. So if you went through the first derivative test with this function, I think you would think that you would get a critical number at 0. You would think that would be a turning point, but it turns out to not be a turning point, but it is an inflection point. This is not a turning point just because you have a wiggle. It's decreasing and it's still decreasing. So 0, 0 is not a turning point. Decreasing to the left and decreasing to the right. So it didn't change direction at 0, 0. Okay, all right, so well, we're out of time there. Okay, so you learned a lot about graphs today. Let's see, this one was concave up. Concave up, let's see, from minus infinity to minus infinity to 0. This part was concave up. And then again, concave up from 2 to positive infinity. And then concave down, well, in the only other possible place, right? Between 0 and 2. Concave down between 0 and 2. Okay. All right. Well, y'all think y'all can go through that? Y'all think you can go through that process? Okay. So it's kind of a lengthy process, right? But it's all just exploiting the first derivative or the second derivative, right? Okay. Well, that's going to be the point of the homework. All right, so well, we've run out of time, right? So remember, tomorrow at noon, right? Madison's going to have a session tomorrow at noon with Madison, and you can use that as a chance to answer questions about your second test, right? Because your makeup opportunity will be Thursday at 1:15, right? And so, and then due on Friday, sometime Friday afternoon. So make sure that you reviewed your test number 2, right? So that if you want to try that, if you want to attempt that makeup, it's optional. But if you want to attempt that makeup, right, you can perhaps add some points to your test number 2 score if you score 70 or better on the makeup. So you have to prepare for that makeup, right? Okay. Because you won't just get points just for attempting it, right? You have to actually make a decent effort. Do y'all have any questions before we quit here? We're just at 1:15 according to my clock.
I have a question, Professor.
Yes.
I missed the first 10 minutes of the class. Like my Wi-Fi was down. Did I miss anything?
Yeah, so Thursday at 1:15, I will post a makeup opportunity. So it's a kind of a shortened version of test number 2. So you can work that just like the test and email it back to me, right? Okay, it will be due sometime Friday afternoon. When I post it, it will have the due time sometime Friday afternoon, and then that will and then that can, if you make, as I mentioned there, if you get 70% of the points on the makeup, that can add points to your test number 2. It depends on how well you do on the makeup, and also what your test number 2 score was, right, as to how many points you will get on that.
Okay.
That could pull you to, that could, depending on your test score, that could boost you a letter grade or more. Okay.
What time the test is gonna be posted again?
Right after class on Thursday, 1:15, just like the usual, usually the way we do it, right?
All right, thank you, Professor.
Yeah. So I'll mention this again on Thursday, but that's when it goes up. Okay. Other quick questions like that. So remember, you have a homework due tonight. It's about limits. All right. Well, okay. So we're done. Let me stop the recording.